Hello, everyone. My name is Anastassia Shaitarova, and today I will talk about cross-lingual transfer learning approach to negation scope resolution. Well, why negation? Because it's actually one of the most fascinating phenomena in language. First of all, it's universal. If we have a language, we can assume it has negation. Negation is very important. It changes the meaning of text, influences the reliability of text mining results. Negated information should either be discarded or presented separately from factual information. Also, negation is frequent. It depends on the domain and genre, but from what I've seen in the data and the literature, number of negated sentences can go up to 35% of the data, which is quite significant. And of course, negation is very complex and diverse in the way it expresses itself in a language, and even more so cross-linguistically. Negation detection plays a big role in many downstream tasks. Here I'm giving just a few citations, but all the researchers report that results improve once negation is addressed. Negation detection has two main steps. Here we have an example sentence. There is no evidence of COVID-19, but PSP is not ruled out. The first step usually is to find special linguistic markers that signal negation. Here we can see right away the words no and not. These words are called negation cues or triggers. Cues can be of several types. Lexical, meaning just single words like no or not. Morphological cues like the suffix less in a word helpless, or they can contain multiple words. And actually, the word not here is a part of a multi-word expression frequently used in clinical texts. Not ruled out is considered a pseudo-cue because it doesn't actually negate. The second step in negation detection is the resolution of scope. This is the step we're interested in. Negation scope is the part of the sentence that is negated. Here, it is evidence of COVID-19. It is affected by the cue no and is negated. But how is scope usually identified? As we can see, it is a span or a sequence that is governed by a lexical or a syntactic unit. One of the established ways to resolve negation in clinical texts is to use a rule-based algorithm called NegEx. It uses a list of negation cues where each cue has a label that tells the algorithm how the cue influences a scope projection. There are four classes of cues. Cues that negate to the right, like no evidence of. Cues that negate leftwards. Terminator words that stop the scope. And pseudo cues that are ignored by the algorithm. So cues are matched from the list, their behavior is identified, and finally, the size of the scope is determined by predefined, simple, regular expressions. Here, the first rule is for the cues that negate to the right. Everything between a cue, a terminator word, another cue, or the end of a sentence is marked as scope. And there's another similar rule for the leftward cues. And thus, the scope is identified. One of the good things about a simple rule-based approach is that the rules are essentially language agnostic. So the algorithm can be adapted to other languages. Most of the existing negation research for French, in fact, involves some type of variation of NegEx. Since I've been working with a French corpus and it has clinical reports, I decided to use NegEx also. First as a baseline and also to see how well it performs. Here's my clinical text. Scope rules remain the same, but cues have to be either translated or written anew, and that can be problematic. It is good to know the language and preferably the domain also. I procured a ready-made list of French negation cues and used them with our corpus first as is. The result was suboptimal, less than 50%. Then I collected the cues from our corpus. So I could, my knowledge of French is decent enough. There are only about 700 plus sentences in the corpus. So I could look through the data and determine the directionality of cues based on my observations. For example, to identify that negative negates to the left. The result improved significantly, but it was still not entirely satisfactory. Of course, even with all the cues available, the scope, the definition of scope is just too rigid. To solve this issue, people have used syntactic methods. For example, the traversal of constituency trees. It was established also that true negation scope tends to trace the boundaries of a constituent. Here we have a sentence. Patient denies chest pain. Slight tachycardia is detected. Denies is our cue. NegEx would have marked everything after denies as scope, which is wrong. At the same time, we can use a very basic rule where we look at the cue and then identify the closest common ancestor between the cue and the next word. Here it's a verbal phrase. Then we mark all the other leaves of this node as scope. This is a very basic approach, but it can still solve many issues, though this approach will suffer if a sentence is syntactically incorrect. Dependencies, on the other hand, are based on a binary relationship between tokens and can handle our more flexible word order. So dependency parsing has been used a lot for negation. Here, this sentence is taken from a Spanish corpus that I've worked with. The negation cue here is sin, meaning without. Jimenez Zafra and her team have established dependency rules for a number of Spanish cues. For example, sin, according to the rule here, negates all children and all trees formed by them until reaching leaf nodes. Here, if we look at our dependency tree, the only child of sin is duda. So this is what we negate, which makes sense because sin duda means no doubt, and the rest of the sentence is actually not negated. So all these discoveries made by the rule-based approach have been successfully implemented by machine learning approaches as well. Cue types and parse tree information have been used as features by various classifiers like SVMs and CRFs with good results. Recursive neural networks have been used because of their ability to model syntax trees globally. Since scope can span in both directions, BioLSTMs have been used and performed very well too. But then, of course, we have transformers that outperform the state-of-the-art on many benchmarks. At the end of last year, Aditya Handelwal and Suraj Savan released NegBERT using BERT for negation. They tested this approach with the 3 publicly available negation corpora in English. The Sherlock corpus has literary texts, Bioscope contains scientific biomedical articles, and the SFU review corpus is a collection of free text product reviews. The results showed significant gain on each corpus. And also the results were good even when tested across corpora, which shows that BERT generalizes rather well. We used the NegBERT architecture, but implemented the multilingual BERT model to try out zero-shot negation scope resolution. This model has been pre-trained with the same masked language model objective as BERT. No parallel data has been used, just large amounts of raw text from Wikipedia for 104 languages. Here, what you're looking at here is the model's cross-lingual shared word piece vocabulary. There is a hypothesis that multilingual BERT generalizes across languages with the help of a shared representation space that is mapped to this vocabulary. The implication is a so-called co-occurrence ripple effect, where generalization starts with such common word pieces as numbers and URLs and continues through recursive co-occurrence. However, some studies showed that the word order of the source and target languages has a bigger impact on the model's outcome than its shared vocabulary. So we've worked with English, French and Spanish, languages that are rather close to each other syntactically and sharing a similar word order. We're in two small experiments. For zero-shot transfer, we fine-tuned the model on all the same English corpora separately, share like bioscope SFU, all the English corpora together, the French corpus and the Spanish corpus. Another idea was to see if fine-tuning just on 100 sentences would be worth considering. And then we tested the models on the subsets of the French corpus and the Spanish corpus. And here are some of the results. The rest can be seen in the paper. The best zero-shot transfer was between the combined English data and the French corpus, with an F1 score of 84.73%. The minimal training data experiments also went well, as we can see, 83 plus for French, 82 plus for Spanish. These results are very good. However, I was a little surprised that Spanish did not perform better. None of the Spanish zero-shot tests ever crossed the 80% threshold. I performed a more extensive investigation to see what might have caused the difference between the French and the Spanish results. And there are multiple aspects that could have affected the outcome, including annotation differences between the corpora. This issue has been discussed by many researchers. I will briefly talk about two other aspects. First is diversity of cues. This table shows a cue distribution of the 5 corpora that I have worked with. We can see that the number of unique cues in Spanish exceeds all the others by far. Even if we combine the unique cues of the English corpora, the Spanish corpus is the most diverse. Many cues in Spanish are multi-word expressions that do not appear in English and appear in the corpus only once. Another aspect is lexical overlap. By lexical overlap, I mean the number of shared subword units between the source language in the training data and the target language in the test data. Here, the left side of the table shows a general overview of the vocabulary size measured in full tokens and in subword units for each language set. We can see that breaking up tokens into subwords reduces the size of the vocabulary. The right side of the table shows the actual overlap. We can see that the French set shares half of its vocabulary with the English set, while the Spanish vocabulary overlaps only by about 1/3. So this might have influenced the results as well. All in all, the experiments went well. While we can't do anything about the disbalance of the cue distribution, other aspects can be improved, at least in theory. A larger corpus with a generalized annotation scheme is long overdue for negation detection. Possibly also it should have universal dependencies. The lexical overlap issue can also be solved by a larger model vocabulary. In fact, there is already another model that is publicly available. XLM Roberta has a word piece vocabulary size that is twice as large as BERT's and should be tried out for negation. But this is it for me for now. Thank you for listening. Now we can say that negation is solved, perhaps. Thank you.